Everyone can see my screen? Hello?
Yeah.
Yes, Professor.
Good, thank you. So going forward, right? So I've been asked by some people like last week if I can have hold earlier, right, in the day, because it seems Wednesday midnight is a deadline, right? Okay, for most of our homework, it seems. Okay. It's probably better that way for you guys, so that once you get some hints or ideas to clarify your thoughts, right? Okay, then you can potentially have at least reasonably good amount of time before you can kind of get to the submission, right? Okay, so that's one thing. The second is, I think, the midterm, right? Okay, it will be right after the lab. Okay, right? And like we realize in the course of schedule of things, right? Please start this homework early on. Okay, it will be really useful and it will make you learn a lot of things, right? It kind of extends on your lab you had in last Friday. Okay, right? Okay, more importantly, there is also a survey, right? Okay, please try to fill in that survey, right? I think this class has gone through. Did you guys get link for the survey on the Piazza? I mistakenly posted on a wrong Piazza, by the way. So just wanted to check in with you guys, right? Did you get the?
I think I saw the post. I don't remember if I filled it out or not, but I think I did.
Sure, sounds good. No worries. That's great. So that's good. So everybody try to fill it out, right? It's anonymous, right? And will be good to get some feedback for us, okay, as to how overall we are doing, right? That's that. Any other comments, concerns, questions?
Professor, I just have a quick question. So
Right.
I was going through the notes and I saw that for the multi-tone system setup, when we are looking at the bandwidth, it's f of n minus f of 1 times n over n minus 1.
Right. This is just to adjust for the MATLABs. When I call it 0 to n, right? Okay. Right. It's rather there are n plus 1 points here, right? Okay. So we can refer this to as 0 to n minus 1 if you want to be clear. That way, then you can have this notation going. Okay. Right. So yeah, I think we can post a clarification for that. Okay. So, and that's something we have been like consistently found out, like Ish can also comment onto it, right? But yes, I think I can address and make a post for that. Okay. And just to explain.
Yeah, I can update the notes. I think it was not very clear. So I will update it. What you said is now clear. I should be clear now.
Yeah. Okay. So thank you, Ish. Okay. All right, let's get started. Sorry. Going forward, right? So let's just quickly recap the process, right, which we learned, right? Okay. So our process is of transmitting, right, getting signals back, receiving them, right? Okay. And then essentially once you get this received data, right? Okay. This data is then, what do we do first? Conjugate. And as you studied, right, I think you can do this conjugate, or you can more specifically conjugate this term from here. Okay, y of t. Okay, right, either ways doesn't matter, right, in the sense that basically what you can do is in the lab as you studied, right, there was y of t conjugate times x of t instead of y times x conjugate, right? Instead of this, right, in the lab we did y conjugate times x of t. The way to think about that process, that once you get y times x conjugate of t, you can essentially do a conjugate operation here, right? So let me just explain, right? So once you have this, right, you go through an ADC, right? Or no, not ADC, right? We go through a filtering block, right? Beta filter, right? Which is essentially trying to kill the nearby reflector, as you kind of went through this in the lab, right? And then essentially you go through an ADC, right? Let me draw this as a triangle. Typically, that's how people draw ADCs, right? Okay. Or generally it's other way around, right? But still, let me just draw it very nicely. Okay, this is your ADCs, right? This is just to show tapering side has one single input and this has many inputs, right? But this is now a complex AGC, and then you can apply a conjugate operation here. Okay, right? That way you kind of can do this if you want to really, okay? But I think we are trying to do this processing, okay? So we are kind of gonna keep it to that, right? Okay. So in a sense, right, you get ADC samples, right? And then you process through, what is the first process we do, guys? Folks, any ideas on Keshav? How about you? Can you tell us what is the first thing we process and how do we process?
We analyze the phase.
No phase, right? We just take the FFT first, right? Correct? To get to, come on folks, this is your, what is this samples here? H of NTS,
Yes.
right? This is H of T, right? Okay.
And that gives us the F of D.
Yes, F of K tau, comma, capital LT, right? Which is basically to say, explain which jerk number it is, okay? Right? Everyone with me? Helena, following?
Yes.
Okay, good. So now once you have this, right, you essentially process that. You analyze this, let's call it time series with L, right? Okay. Right. So the analysis of this time series yields what? Could be breathing heart rate, right? Okay. Or could be human motion, right? Okay. And so on and so forth, right? You can build whole host of applications by post-processing this data, right? Okay. So we are going to focus on these two, but you can build many more things beyond this as well. Okay. Does that sound good to you guys?
Professor, can I ask a question?
Go ahead, go ahead.
So when the human is moving and we analyze the time series, would we still be able to then tell the difference between breathing and heart rate, or do we need the human to be static?
So I think for now we are assuming it to be static, right? But there are ways where we can kind of even use some other information really to abstract and remove out. So think about this as an example of following, right? If your breathing and heart rate, right? Okay, they are both concurrently observed, right? Okay, can we separate one from the other? We can right now, right? And why can we separate them? The reason we can separate them is because breathing rate and heart rate are at fundamentally different frequencies, right? One is from 0.2 hertz to somewhere between less than 1 hertz or 0.67, right? Okay. And other is 1 hertz plus to somewhere between like 3 hertz or 4 hertz, right? Okay. Worst case scenario, right? So that's how we can kind of separate, right? So if turns out that human motion don't fall in each of these bins, right? Then we can potentially try to separate that out and remove that out as well. Okay. So think of this as superposition of signals, right? You can remove it if the human motion follows certain behavior like this. Okay. Does that make sense?
Yes.
Good. All right. So going forward, right? Okay. Just the same process, right? Okay. What we discussed the other day is that here, right, at this point, as you can see, let me highlight this, right? This point here, right? Okay. You can take another FFT, okay? But this FFT goes across, what does this FFT goes across? L, okay? So this next FFT we conduct, right? It goes across L. Everyone following me here, right? So basically the output of this first FFT here, right, is FK tau, comma, LT, right? And now you take FFT across L, okay, as we discussed in last time, right? So earlier what you took FFT across was H of NTS, let's call it LT, okay, right? I'm just, it's h of NTS. Just, I think I'm just saying that I will separate each chirp out here. Okay. I took the first FFT across N, right? NTS, right? For all NTS, for all values of K, L. So essentially what I'm doing is I took the samples I received here, right? Okay. And arranged them in time series, right? Okay. From 0 to capital T, then from T to 2T, right? Okay. And for each time I'm taking this small FFT first. Okay. Right. This gives me what? F of K tau. Okay, guys. All right. Everyone following me here? Keshav?
Yes,
Sorry,
Professor.
I'm following and picking up on Keshav too much. I gotta pick on someone else. Okay. So going forward, right? We keep on taking FK tau and keep on doing this FFTs for different blocks of this times, right? And essentially we get those FFT outputs, right? For all these time slots, right? And once you have this entire big FFT array here, right? So let's say so far you have been taking FFT across this, right? Okay. Now we'll start taking
Professor, did the
vertically the
screen
FFTs.
freeze?
Sorry.
Did the screen freeze for anyone else?
No, I think it's still working for me at least. Is this frozen, folks?
It's working
You
for
see?
me.
Sorry.
Is it moving up and down?
Yeah, it is now.
Okay. Thank you for reminding me. If that happens, let me know, please. Okay. So basically, then we take FFT across the other dimension, right? Okay. And that yields us on one side, it's essentially K tau, right? The range, right? Okay. And other side, it yields frequency of oscillation, right? As we were briefly discussing, right? Now, I think we will cover this concept a little bit more detail, but I just want to give you a high level processing, right? And then we can use this kind of separation in frequency to kind of recover breathing and heart rates. Okay. But let's go back to more simpler approaches and why do we need this approach? And that's what we are going to cover in today's class, right? How can we do static multipath suppression, right? Okay. And then essentially analyze those and get some intuition first behind that. And then we'll build on to that to go to the Doppler as well. Okay. So, so let's model the static reflection with FMCW. Who wants to give me some ideas on how to model this? So let's go to the basics, right? What is our basics? H of NTS, right, is nothing but, come on guys, let's see who can tell me what F of NTS is. Some exponent component, right, which has phase of F naught tau, right? And then next component which has frequency which is proportional to K tau, right? Okay. And this, sorry, this K tau NTS, right? Okay, is summed over all the different paths, right? So we can call it di tau I, right? Okay. And this is potentially for each path I from 1 to L, right? Okay. And we came up with the first Fourier transform, which what it does is that it's h of NTS exponent of j k 2 pi k tau NTS, right? Summation over, what is the summation over here, folks? How about Dylan?
Summation over all your lambdas.
No, N, come on, folks. We cannot keep making mistakes, okay? This is FK tau, right? Sorry, let me write this from this side. Does that make sense, Dylan?
Yeah.
From 0 to T here, okay? Basically for one particular chirp, right? And this, for example, I can say it, comma, LT, where L is 0 here in this case, okay? Make sense, Dylan? Because the time goes from 0 to T here. Dylan, following?
Yeah, I'm following.
Okay, so let's just write what of f of k tau should look like. F of k tau should look like summation of I equals to 1 to L, all the paths, right? Basically peaks corresponding to those paths, having amplitude of lambda times di, right? With some additional phase, exponent of j2 pi f naught tau y, right? Plus delta of ideally k tau minus tau I, right? But this is not actually this, right? What is fk tau in this particular case? It will be sink, correct? Everyone with me? This is the results from the previous class. Helena?
I'm following.
Good. How about Eric? Is Eric here? Okay, he's not here.
I don't think he could come to class today.
No worries. Puneet, making sense? Puneet, you're still here? I can't think we can't hear you. Maybe you can use chat, okay? But everyone follows this, like the delta versus the sink thing, right? Guys, right? Yeah, I know. I think this just has been done in one of the previous classes, but I think everyone needs to have like this and like really built into their hearts now, okay? Really embedded into you. So now let's take an example of two paths, okay? The one which has so you guys studied in your lab as well this last week, right? That if you have two paths, right? Let's call it one path corresponding to D1, right? Which is tau I, and let's call it sink here, okay? And let's call this as tau1, okay? And plus, let's say this is the one which has your breathing and heart rate in it, okay? The tau slash D1 has some breathing and heart rate information in it, right, folks? All right. Now, let's take the static one. This is the static one, exponent of minus j2 pi f naught tau2 sink of k tau minus tau2, okay? So just to plot this, right, so that everybody has an understanding, right? This is essentially you have k tau1 and k tau2, right? And there are sinks associated around it, right? Everyone with me on this, folks? Following me? And this has some variation, right? And this is x-axis is d, y-axis is the amplitude here, okay? Let's call this as absolute, but basically this variation is what has breathing and heart rate, let's say, for k tau1 here, okay? All right. Puneet, following?
Yes.
Okay. How about Dylan?
Yeah, I'm following.
Okay. So D1 is where you have breathing and heart rate. D2 is some fixed path, right? Okay. So now we understood one trick of how to do it, right? So like one trick to doing is just doing subtraction of static paths, right? Okay. Or just doing subtraction of fk tau at 2 time slots, right? So what we're going to do, fk tau comma lt, right? Where L is equal to 1, right? Okay. Minus fk tau comma lt, let's say where L is equal to 0, okay? So just to be clear, right? What happens when L changes here, right? Why don't we write first, let's say this expression, right? As we can already know, right? This expression is for L equals to 0 here, okay? Let's say this is the case, right? Okay. What happens when capital L becomes 1, guys? Why don't we write this expression right here if possible? What will change for L equals to 1 in this expression? So clearly D1 will change, right? Okay. Right? Because your breathing or heart rate will cause it to change a little bit, right? Which implies that tau1 will change, right? What other than that will change?
Your K tau 1 peak will shift.
Sorry?
Your K tau 1 peak, your sync will shift.
Yep, exactly, right? That's fantastic, right? Because tau 1 also changed, the K tau 1 will change and its sync peak will shift a little bit, right? For L equals to 1, okay? Right? So let's do subtraction. In subtraction, what would happen is that this term will get cancelled, correct? Everyone agrees with me? When I do subtraction of fk tau from L equals to 1 to L equals to 0, right? Okay. What would happen here, folks? Right? The second term will definitely disappear. Okay. Everyone, does they need me to write it down? It's clear, right? Keshav? Helena? You guys are muted, so if you're speaking, you need to unmute yourself or need to type in chat message. Can you hear me?
Yeah,
Yeah, I
think
can. Yeah.
Sorry, yeah, I thought maybe I froze. And that's why I couldn't realize that. Okay, all right. So going forward, right? So now this will be left with lambda over, let me call it, so look, the distance will change, but amplitude will be more or less be the same across those two time slots of, even if distance changes by small amount, the capital D1 will be, as we know, consist of three components, right? D naught plus DH sine, right, of something, plus dB into sine of one other thing, right? Okay. So this D naught, this variation compared to D naught will be kind of very small, DH and dB, right? So the amplitude will remain the same, right? Let me write it down this way, lambda times D1, right? Okay. But we'll have exponent of minus J2 pi F naught tau at time instance 0, right? Okay. Times sync of K tau minus tau 1, okay, minus exponent of minus J2 pi F naught tau 1 of 1, or call it 3 if you want to, okay. But this is L index, okay, right? Okay. You can do it other way around. I can call this as 1 to 0, the subtraction, right? Okay. So that way it's consistent, right, with the notation I have used, right? So 1 minus 0 here, right? This is also, clearly there is tau 1, right? And this is just at one instance, right? Okay. Sync of K tau minus tau 1 at 0, right? Okay. All right. So as we discussed last time, right? Look, breathing will cause very small change at the rate at which the chirp is going, right? Even at 100 microsecond rate of chirping, right? Where capital T equals to 100 microsecond, right? Even then, right? These will very, very small amount. By the way, there was another amplitude term, right? Lambda over D1, right? Okay. So I'm not changing D1 in these two because it's 1 over D1, right? As we discussed, they will be more or less approximately the same, right? So the terms here will be approximately same, will be this and this in amplitude, right? How about the sync term? Will it change significantly from one time slot to the next time slot? Keshav? Is everyone clear on this term, by the way, first? Dylan, Keshav, questions?
I think it'll make a very small shift, right?
So let's make quantities which will make small shift, and let's draw them in purple, right? The quantities that will make small shift is this, right? This, okay? And this and this will make a very small shift, okay? The only thing which will make major shift is How about you tell me the one which will make major shift? There's only one thing left, right? This one. This will make a major shift. Okay, the one highlighted in yellow. Okay. So now let's analyze that part a little bit, right? I'm going to do is following. I'm going to take this term out common, right? Okay. So I'm going to call it lambda times d1 of 1, right? Okay. Times sinc of the terms which are common, I'm going to take them out, right? K tau minus tau 1 of 1, let's say. Okay. Right. And there is exponent terms, right? Those get in subtraction. Minus j2 pi f naught tau 1 of 1, right? Minus exponent of minus j2 pi f naught tau 1 of 0, right? Does that make sense?
Professor, what happened to the other terms?
No, they are there, right? It's just I added a big bracket here. So I'm
But
just going to call.
aren't they separate, the other sinc and the lambda over
No, I'm
d1?
just taking those things out common and just I'm calling them like the same value. Let me just call them tau 1 now. Okay. All right. Let me not keep those notations, right? Okay. I said that they are equal in these two, right? And I'm just taking them out common. Okay. Does that sound good?
I see. So the small shift we're saying is small enough to ignore the shift, so we can assume that they're the same values pretty much.
Yes, yes. Basically, that's what I'm arguing first. Okay. Let's understand what happens under that case. Okay. And that's actually kind of the case more or less, right? This needs, for this to be changing, right? The sync, it needs to have a lot of drastic movement, which actually is rarely happens, right? Imagine 100 microsecond, what can you change, right? Okay. The only things which can change at 100 microsecond, which is essentially saying that something changing at least 10 kilohertz rate. Okay. Right. Okay. So none of the human level activities which we try to do can be as fast as this, right? Okay. Like for example, some non-mechanical thing like flights or planes can have this kind of offset, right? Okay. Their motion can have this kind of motion offset, right? Okay. So just going forward, right, with this part of notation, right? Okay. So what we are really left with here, right, is these terms, right? And why are we not saying that these terms will not remain same, Keshav?
Because they're much more sensitive to the small movements, right? So
Yep.
they don't require as much of a frequency to shift.
Yep, exactly, right? Because as we discussed, right, f naught is really large and the smallest change in this kind of still keeps the phase rotation going. Okay, so let's just take another thing, right? What I'm gonna do now is I'm gonna keep sync k tau minus tau 1, right? Okay, and also take another exponent out of the equation, right? I'll be left with exponent of j2 pi f naught tau 1 of 1, let's say. Okay, right? And the rest of the bracket will be left with one minus exponent of, what is it? J2 pi f naught. Come on, folks. What will it be?
Tau 1 0 plus tau 1 1.
No, minus tau 1 1.
No, you're taking it common, right? So you're dividing it by the tau 1 1, and it already has a
Yeah.
minus sign, so it'll become plus.
So then it therefore it's minus, right? Because the minus is applying to entire bracket here. Does that make sense?
Okay, yeah, I see it. I see it.
Helena, does it make sense? Dylan, following me, guys?
Yeah, you
I
just
can-
distributed it out.
Yeah, I can write it out more clearly so that it's clearer. Further more clearer. Okay. Clear on the number of brackets. All right. So let's understand this term now. Okay. All right. So when this, what it's saying is that when these two are very close, right? Okay. What would happen? This term will go to 0. Sorry, not this term, rather this term will go to 0, right? And what will that lead to? That will lead to this larger term becoming 1, right? And what will lead to that larger, furthermore larger term to become to 0, right? Does that make sense? Slightly convoluted, but is that everyone following me? Keshav, Helena, Dylan,
Yes.
Meet, Renji?
Yes.
Yeah, I'm following.
Okay. So now basically when there are small changes, right, or almost no changes, right, then this expression goes to 0, the entire thing, right? Basically it's perfect subtraction, right? Okay, like that is true for static subjects, right? But when it goes smaller, larger changes, right? Okay, this expression can go to, let's say this entire expression here, right? The phase rotation, right? Right, this phase rotation instead of 0 goes to, let's say, pi. Okay, right? What will that lead? That will lead to -1 instead of 1. Okay, this entire term will become -1. So 1 minus -1 is 2, right? Okay, so this will have maximum amplitude twice. Okay, right? Everyone following? So the minimum value of this thing is 0 and the maximum value of this expression is 2. Okay, right? So let's just do one example here. Okay, one example is following. Okay, I'm going to draw here time. Okay, and this is your d, y-axis. Okay, so I'm plotting d of t, right? Okay, so let's say this is d of t, right? At 0, at time t, at some time 2t, and let's say some 3t and 4t. Okay, right? This is 3t and this one is 4t, let's say. Okay. All right. So what happens between 0 to t, right? And let's remember this is d0, right? Okay. So this is like not 0 as such. The d on y-axis is d0, and this d goes over time, right? And as you can see, for example, let's take this as a breathing, for example, right? So d changes between 0 and t time slot, right, on x-axis, right, by significant amount, right? Okay. So if I were to hypothetically plot just this expression here, okay, right, specifically this expression here, right, okay, how would it look like? Anyone want to guess? So it will have a large shift, okay, right? When from 0 to t, it has a large difference, so it will have a large shift, right? But when it goes to 3t or 4t, right? Look at the 4t one, right? They have almost the same value, 3t and 4t here, okay? In that case, this will go to 0 under like 3t or 4t case, okay, right? And similarly, basically, whenever this has a sharp transition, which is where here, for example, right, it will take large values, right? It will be something like this, right? Okay, and this goes from where to where? Come on, folks. This goes from, this value is, oh, my bad, sorry. I think my bad on that front. So it goes from 0 to 2, right? Okay, so let me just draw it this way. This is your y value is 0 here, right? And this is your 4t time or 3t time, however you want to call it, right? So it will go from 2 to 0, right? And then again back to 2 and 0 and so on and so forth, okay, right? Whenever there is a large change, right, it will go back to, let's say, 2, for example, here in this case, right? Again, we don't know if it will go to 2, but it will go to some large value less than 2, okay? Everyone following with me? Helena, Keshav?
I'm following.
Yes, I'm following.
Good, good. All right, great. So now that we understand this phenomenon, right? Okay, so really, what is interesting here? What is interesting is that the subtraction after you do it, this is, what is this? This is gets multiplied with your amplitude, correct? Right? Does it make sense, Keshav? What I'm saying?
I don't think I got the last part.
So what is happening, right? As D changes, right? The amplitude of this is the differential signal, right? Okay. So just to give you a sense, right? When we are doing the subtraction, right? Okay, right? We can subtract two time slots, right? Okay. And what it allows us, right? Okay, is to see the signal in amplitude, okay, here. So just to rewrite this expression, if I have to, right? Let me rewrite this expression, maybe a little bit more, duplicate the page, duplicating. Okay. Sorry, what did I duplicate the right page? Okay, not exactly. So all right. So just now that, yeah, we have got the duplication going. So let me just write down this now. Okay. Just erasing a few things here. Okay. This is your expression, right? For, let's call it now G. Okay. What I'm going to write this as G of K tau, comma, LT is nothing but F of K tau, comma, okay. Everyone with me? Right? So G of K tau LT is nothing but lambda over D1 sink of K tau minus tau 1 of okay, multiplied by 1 minus exponent of minus j2 pi f naught tau 1 of, come on folks, tau 1 of,
0.
sorry, what is 0? 0 becomes L minus 1, right? Does that make sense? This is L minus 1.
Yeah.
Yeah.
Right? And tau 1 of L. Let's make sure the brackets are done right. And then this is square bracket.
Won't there be a capital T also?
Yeah, it will be. I just dropped it for fitting it into the line. Okay. Thank you for clarifying. Right. So there is L1 minus 1 times of T right here. Okay. I just drop that T term so that it fits in well, okay, in the line, single line, okay. All right. So now we understand the G, right? Okay. Does that sound good to everyone?
Yes.
Okay. Okay. So now that I have G term, right? Okay. So the observation I made and tried to make is the amplitude of K tau, right, at G's expression, right? Okay. It has an interesting behavior. The amplitude goes up and down with this particular behavior, right? Here, this is essentially, you can think of, this is nothing but amplitude of G at, let's take a specific value of K tau 1, right? Okay. Right, as LT, right? With x-axis here is L times T, by the way, guys. Okay, right? So at 4T, right? Okay, this expression goes to 0, right? Amplitude goes to 0, right? At, let's say, time slot 1, the expression is at, say, somewhere value 2, for example. Okay, right? The absolute value, right? Let's imagine this case, right? Does that agree with you, Keshav? And everyone here, rather Dylan?
Yeah, this is just your amplitude function.
Yep.
Over time.
So what is the benefit of having amplitude varying with breathing, for example, here? Sorry, Dylan, you were saying something?
Can you repeat your question?
So what is the benefit of having amplitude change with breathing?
Well, now we have a better option of either choosing phase or your amplitude to try to extract the breathing.
Yep. So you can use amplitude to extract breathing, for example, right? Okay. Sorry, yes. And you can use phase to extract heart rate, or can you still do that or no? So let's examine this term a little bit more carefully. Okay. Right. So as we can understand, right, now the interesting part is amplitude is super nice. Okay, it's varying with breathing rate. Okay, right. Now as we understood, right, you could extract this, and based on that you can kind of like try to get breathing, right? Okay, or at least the variation in breathing, right? Everyone with me on this? Or people have questions, clarifications? So this is kind of like, let me connect one dot here. Okay, I kept on asking, and I have been asking this for a while, right? If I have only single wavelength, right? Okay, remember this plot again for your D, right? Okay, and essentially if you remember this plot, right? Okay, so for 0 to lambda by 2, the phase remains the same, right? From 0 lambda by 2 to 3 lambda, again the phase starts from this, right? There is a wrapping here, right? So some similar sort of wrapping is going around here as well, by the way. This term is wrapping around itself, right, in some ways. But just subtraction is just exposing at least the wave nature of the breathing, okay, right, with more coarseness, okay, if that makes a little bit sense here. If it does not, I think just forget this term, okay. Just I'm trying to connect back this one dot, okay. But let's go back to examining this term, right? If I take G, right, okay, there are two interesting things happening with G, by the way, right? One, we understood that amplitude has nice features, right? It can kind of help you with getting breathing rate nicely as well, okay? Right? It essentially goes up and down, right? Okay. At the same time, the exponent also carries this phase term, correct? in a way, you can kind of leverage both those signals, right, to get breathing and heart rate. Okay. Everyone with me on this?
Yes.
So you can look at the phase term to get the heart rate, and you can look at the amplitude term in this case to kind of get a good crude sense for breathing. Okay. Sorry. Into my eye. Okay. So now this is what were we doing so far? Okay. See, I think one thing. So I was hoping to maybe. So one other idea or trick you can do here is you could kind of do in. Let's not go to that 50. Okay, but let's see now. So far, what have been we subtracting, right? We have been subtracting in. Where are we subtracting this, Keshav? Come on, folks, quickly.
Professor, do you mean which stage we're subtracting?
Sure, stage will give you, I was more specifically talking about domain, right? Okay. We are subtracting in k-tau domain, by the way, right? Okay. Or frequency domain right now, you can call it, because, correct? We subtract after taking the first, well, let's not call it FFT, okay? Why should we not call it FFT, Keshav? It is?
DTFT?
Yep, thank you. Does that make sense, Helen and Dylan as well? Sorry, Elena and Dylan. Sorry, my bad.
Yes.
So
So
this
you're
is a
you're
DT.
subtracting.
Sorry, yeah.
So you're subtracting frequency domain signals, but over time, right?
Yep, yep. So you're more specifically, you're taking for FFTs for short duration of times, right? Okay, and then subtracting them across time as you go along, right? Okay. So just to be clear, right? Going back to this figure, let me just show you this figure again. Okay. Sorry, what happened? Okay, yeah. This figure, going back to this figure, right? This is the short duration of time during which I took an FFT. Okay, let me use an highlighter here. Okay, I took the FFT in this domain, I took FFT in this time slot, FFT in this time slot, and I'm kind of subtracting the FFTs of those. Right, Dylan?
Yeah, exactly.
Yep. So it's like you can call it short time Fourier transform subtractions, okay? If that's something which helps you in thinking about this way, okay? Right, okay. So a question for you, right, okay? What is the problem with doing this kind of subtraction, by the way? You could do FFT based subtraction as well, right? Okay, but FFT becomes a very crude, right? Because then this will be discretizing furthermore in this, the sink will get discretized, right? Okay. So you can do FFT subtractions, by the way, and you can see and observe that you will see the similar behavior going on, okay? But right now, what all the analysis we have done is for DTFT subtraction, okay? Right? Can I do more simpler thing? Like, does it matter if I do frequency domain subtraction or I do in sample domain subtraction? There is a hidden question, folks, here a little bit, but sorry, go ahead. Keshav, Helena, what is the other kind of subtraction I can do other than FK tau? Puneet?
We can take FFT across chirps, and then if the reflection is static, if we take FFT, it will be a DC, so we can directly subtract it from there.
Yeah, I think that's maybe jumping the gun here. There is a more simpler technique to be applied. Okay, The simpler technique is, and I think ideally subtracting in DTFT preserves all the information, right? Subtracting in FFT doesn't preserve the information. Okay, there is some loss of information in FFT subtractions. Okay, more specific to the point is that because the sink may be shifting a little bit, right? It can create some non-zero component just because of the sink shifting in the FFT. Okay, rather a more accurate and a more nicer way to do the subtraction is in sample domain, by the way, guys. Okay. So let me jump and explain. Does everyone understand what sample domain subtraction is? Anyone who can tell me what sample domain subtraction I mean hereby?
Professor, I don't think I understand what that means.
That's okay. But why don't you tell me what is the other domain where you can do this subtraction? Is there any other domain where you can do this subtraction? Forget sample domain subtraction. Or you didn't understand the FFT and the DFT, DTFT part? Hello?
I don't think I understood why there's a loss of information in FFT.
So I think that's a maybe more involved topic, and it's better done in a lab and then
Okay.
here. Okay. Let's go back to the question at hand. Is that what is the other domain which we can do subtraction in? Can you guys hear this weird noise from my end? Hello? Eric, Dylan, Keshav, anyone hearing some weird noise of some guy trying to move lawn outside?
No, I don't think I can hear anything.
Okay, good, great. Thank you. That's great. So here the idea really is following, folks. Okay. The idea is to kind of like basically this DTFT and FFT, right? Okay. It's probably complex. DTFT is definitely complex to compute, right? FFT subtraction doesn't preserve information, right? What is a way to do subtraction which will preserve the information and still won't cause any problem? Which, come on, folks, quickly. Keshav or Helena, anyone ideas? Let's write down the process, right? You get received samples, you get conjugate multiplication, right? Okay. You do high pass filter, right, with beta, right? Take it through an ADC, right?
Professor, I think your screen's frozen.
Oh, thank you. Sorry for, yeah, thank you for informing. Can you see?
Yeah, that's better.
Good. Thank you. Thank you for informing about this. Okay. So you do filtering of beta, right? And once you get these of H of NTS, right? Okay. You do FFT and you get to F of K tau, right? Okay. Now, one way to do in a discretized K tau, right? Okay. One way to do is do the subtraction here, right? Okay. Correct. That's what we are showing up here, right? Okay. Between two chirps, you do subtraction here, right? What is the other way to do it? Dylan?
I'm not sure.
Any idea, guys? Okay. So let's maybe write it more. How about here? Can I do the subtraction before taking FFTs? Let's quickly revisit how H of NTS looks like. Okay. This is how your H of NTS looks like, by the way, guys, right? Sorry. So sorry, guys, just give me 1 second. Somehow the copy paste is not exactly the way I would like to. All right, so this is how your H of NTS looks like, okay, right? Right, let me maybe make it more specific, right? H of NTS, right, with L comma T, okay? More specific to the point, right? This H of NTS, right, can be rewritten. Let me write this as this way: H of NTS comma LT, right? Okay, lambda over D1, right? Exponent of minus J2 pi F naught. I'm just going to write L. I will drop the T and assume there is always the T. Okay, this is for tau 1. Okay, plus exponent of, sorry, not plus, minus exponent of, first let me complete the first term, right? K tau 1 of L comma NTS, right? Minus, not minus, plus lambda over D2 of L, right? Exponent of minus J2 pi F naught tau 1 of L, or sorry, tau 2 of L, my bad. Forgetting, exponent of minus J2 pi K tau 2 L times NTS, okay? So this is for L equals to 1, right? You can do L equals to 0, right? And you can subtract them, right? If you subtract them, right, what will cancel out, folks? This term here, right? Okay. This will, if I define G of NTS comma LT is equal to G of, oh, sorry, not G, H of NTS okay. Everyone clear on this? Any questions? Should it work or should it not work? Questions, Dylan?
No, I understand what you're doing. I'm just thinking about how the FFT looks now.
Sorry, what are you thinking of? FFT?
Yeah, for the next step. So now that you've done the subtraction before your FFT, so between the ADC and the FFT.
So what I have done technically, right? Let's show it on a block diagram. That will be clarify a lot of things. Okay. What I have done essentially, right? I have pushed the subtraction to here. Sorry. I have pushed the subtraction here. Okay. Pre-FFT. Okay. Now what I can do is I can take this FFT of this G, right? Okay. And that will give me the, and let me just make notationally one thing correct, right? Let's call this one as capital G. Okay. Sorry, I should have done it earlier. Sorry, I thought I had made a note of it. But let me define this as capital G. Okay. All right. Hopefully you guys, yeah. Let me just say this is capital G, right? So that it's clear, right? That it's a small g is non-Fourier and capital, like you now take this capital G's Fourier, right? But before I take the capital G's Fourier, let me write down, make sure to write down the mathematical expression form for the G, okay, right? So it's clearer in a way, okay. So G, somebody want to give me the pointer on how to write G, expression for G? How about somebody giving me a trick here? This is nothing but, it will have, for example, just term corresponding to D1, right? Okay, of Let me write this way. So when I subtract two things, right? Okay, let me just complete this term first, and then I will give you how it came down to this term, right? Again, I'm dropping capital T from L whenever there is L. Just assume that there is L times capital T. So somebody want to take a hint on how so this subtraction went away, which we got because all of these terms will remain same across two time slot, right? What term will change? Come on, folks, quickly. So capital K times tau, right? Even though K is a large number, right? K times tau still is a small number, right? Compared to F naught into tau, okay? So the point I'm trying to make is following, folks, okay? This term here, right? Exponent of J2 pi F naught tau 1 of, or let me, let's just write it down so that it's clearer for everyone. Otherwise it will become more unclearer than becoming clearer. Let me write down both the terms so that you can understand the subtraction part much better, okay? Okay, does that make sense, everyone? Now tell me which terms will cancel out, which terms will stay back, right? Okay, so this tau 1 is function of L minus 1, right? Okay, gets multiplied by capital T. The frequency still will remain same as this, okay? Right, that's first assertion here, okay? It will change very small insignificant amount, okay? It's like your sinks remaining the same more or less, okay? Same thing goes for this term, right? They will remain more or less the same, right? Okay, and what you will be left, right? Okay, will be the phasor term, right? Which is essentially what we examined earlier on, okay? So let me just write this for the sake of completeness, right? Exponent of minus J2 pi K tau 1 function of L, let's say, okay, NTS, right? Times 1 minus exponent of, oh wait, another term, sorry here. Exponent of the phasor term minus J2 pi F naught tau 1 of L, right? Okay. 1 minus, okay, exponent of somebody want to complete this for me? This is a slightly longer term, so I'm just continuing this term here. Tau 1 of L minus 1 times tau 1 of L times NTS. Rather, this is K, sorry, my bad. No, not sorry, my bad. This is K here. This is not here, that was correct here. Everyone with me? Keshav, sorry. Following me here? Dylan, Eric. Sorry, no, Eric is not here. Dylan.
Yeah, I'm just trying to go over the math.
It's fine. The point is that the math remains the same. I'm just taking out the terms which are common, right? This was the term which was more or less the same in these two, right? Okay. I took that term out same. This term is also same, right? I took that term out, right? What were left were only this term and this term were left, right? Okay. I took this term out common, right? This is your common term. Then that becomes 1 minus the rest of the expression in exponent of j2 pi f naught, right? Which is tau 1 of L minus 1, right? Minus tau 1 of L, right? So all of this exponent business is one single exponent. This is equivalent to, let me maybe clean the second line up, that way it's clearer, okay? So let me clean this up a little bit here, okay? So this is f naught of tau 1 into tau 1 of L minus 1 times tau 1 of L times NTS, right? That closes this bracket, okay, right? And the big bracket, okay? Everyone with me? The exponents bracket is closed here, guys, okay? That's the point I want to make, okay? So is this now more clearer? So this subtraction term, right? From this here, right? Okay. And here, right? That essentially is what stays here. Everyone with me? Dylan?
Yeah, I see what you did.
Keshav?
Yeah, I think that makes sense.
Okay. All right. And if you find any corrections or mistakes in my writing, right, just let me know post class as well, right? If that's something, yeah, I've missed and so on and so forth, we'll be happy to correct. Okay. All right. So now let's just maybe quickly examine this term again. Okay. So the best part of this term, and after you take even FFT of this term, right? The benefit here really lies that, oh, sorry, I had made a mistake. Nobody noticed, huh? Let's see, I'll erase and complete that mistake, correct it. This one here, right? Oh no, that was incorrect, right? Yeah, it is incorrect. Anyone wants to tell me what is the incorrectness here? 2 pi f naught tau 1 of L times NTS. Okay, all right, everyone with me? I'm going to use a slightly lesser thickness pen so that it seems that way the expressions are maintained. So when you take Fourier transform, right, of this, right, what will happen is that this will give you the first term here. This will give you the peak at k tau 1 of L, right? The frequency component is in here, okay, right? Everyone with me? This will give you the phase component, okay? Tell me what this will lead to. The first term, by the way, sorry. Let me not call it. This becomes basically delta of k tau minus tau I, right? Right. This is your capital G function, by the way, right? G of k tau, okay, right? So this will become the phasor term, which essentially has the information regarding heart rate, okay, or more dominant information about heart rate, okay. And this third term here, right, that will be dominated by breathing, okay. Everyone with me?
Professor, I had a question.
Go ahead.
Earlier in the class, we would take the phase and we were able to find both breathing and heart rate.
Yep.
What's the reason for now separating them between amplitude and phase?
I think still the information is in both. So let me correct myself here, right? It's just, as I keep saying, dominated by breathing and dominated by heart rate, right? So you will still see the information of both of them in each other, okay? This process, right, primarily should, like, you should think of this, the things to take from this class, okay? The first is subtraction can be done in any domain, okay? And it leads to suppression of static multipath, okay? That's first message, okay? And how do you analyze, and the math of that is there in this, right? That's the first message you should take, okay? The second message is, right, that, so that I keep saying this phase, and like the second message is that the phase is still retained, right? So phase, what is the benefit of the phase term, right? Look at the phase term, right? Phase term is very much proportional to tau k, f naught tau, right? As f naught tau makes small variation, right? Even those are captured here, right? Okay. But when you do this 1 minus, right? So what it is exposing is that the amplitude has new unique information, right? Because of the subtraction, okay? So earlier we were relying on phase mostly, right? Okay. Now what we are saying is that amplitude information similar to phase previously, okay? That's the second point of this class, okay? So previously phase only had the information, right? Now I have both amplitude and phase have this information, okay? Does that answer your question, Dylan? And makes like all this sense, right? I was trying to make a distinction and domination, right? But I think you shouldn't think of it this as domination. Both has the information on breathing and heart rate. Okay, that's a good question. Thank you for correcting. And just take a note of that, okay, everyone. Okay. So in order to recover breathing or heart rate, you should use both information, and you can use the same analysis which we have been doing previously. Now you can also do that analysis on amplitude. In a way, you can think of the phase information is translated into amplitude, by the way, okay? Because of the subtraction of 1 minus this, right? Essentially, it's like the phase information translated into amplitude, right? Like we were earlier using this information here, right? The exponent of subtraction of, or the variation of tau, right? Embedded with the phase here, right? Across like this Fourier to get the information on breathing and heart rate. Now, instead, we also have this 1 minus term, which kind of gives another proxy of measuring this phase with more amplitude information. Okay. Right. Does that make sense?
Yeah, that was a good explanation.
Yeah, I think thank you for asking the question. Actually, that kind of clarifies the intent of the class. Okay. I see we are at 4:45. So let's just quickly go over the, as we discussed, right? You can take now the FFT of G, right? This is your function of FFT of G, right? Okay. And in the FFT of G, you will still retain the phase information as you were retaining earlier on, right? Okay. And you will kind of see the amplitude of that K tau, or this K tau component, right? Very much going up and down as time progresses, right? Okay. So the point I'm trying to make is that we are still now doing, let me just update the architecture of the receiver first, okay? This is your received signal, right? It goes through conjugate multiplication, right? Okay. Goes through high pass filtering, right? Okay. The beta filtering, right? Goes through ADC, right? Okay. And goes through subtraction, right? Okay. right? Differential subtraction, right? Okay. And that subtracted quantity is small g, right? Okay. Whose FFT we take, and we get to G of k tau, or capital G of k tau, so that it's clearer, right? Okay. Comma LT, right? Now, after you take this FFT, right, what you tend to have is at k tau 1, right? You have this smaller sink, right? Okay, which has amplitude varying with 1 minus the exponent, as we discussed previously, right? Okay, and the phase of this point varying with the phase behavior we have noticed previously as well, right? Okay, and now this will happen, right, for every L T. Okay, so if I had to draw a third dimension, right, which is like going outwards here, okay, let's say this is, let's say your L equals to 1, right? Let's say this is L equals to 2 here. Okay, you'll have the same behavior, you'll have the sink, right? Okay, at the same time k tau 1, right? Okay, but it will slightly vary. Okay, both its amplitude will change, right, depending upon the 1 minus exponent function, right? Okay, and its phase will also change, like what we did, right? So now you can have this L equals to 3, right, and L equals to 4, right? Okay, now you could invoke then another FFT across this axis, okay, across L axis, guys. Okay, everyone following me? Keshav, does it make sense what I'm doing here, what I'm drawing?
Yeah.
So now we can take another FFT, right? And that can be used for analysis as well, right? Okay. Now by taking another FFT, right? Okay. What will we get? Okay. Similar to the last plot, right? Okay. We'll get a representation of range, right? Okay, let me draw it on the maybe next page, right? That way it's clearer, right? Okay. We will get following. Okay, on one side you will have k tau, right? Okay, and on other side, since you took an FFT across L, okay, right, you'll have components across LT and its FFT, right? And this FFT, right, okay, will essentially show you two components. Okay, breathing will be here, right, because it's slow, right? Okay, second, heart rate will be slightly faster, right? Okay, but can be shown here, right? Okay, so more on this. So what I'm trying to say is that you can do the static path and you can apply the same analysis as you were doing previously and extract breathing and heart rates nicely. Okay, all right, everyone with me on this? Now we keep drawing this FFT and don't go into the details of the second FFT. In the next class, we'll start studying the second FFT, by the way. Okay, and how to analyze and how to understand its range and resolution and what does those range and resolution means, right? Can you get those breathing and heart rate here, right? That's something is the question next for us. Okay, I probably, yeah, this is what I mean by invoking the second FFT, right? Okay, right, but I think we'll cover this in more detail in the next class, and the next lab will essentially introduce the delay Doppler as well, or sorry, next lab, which is for your exam. Okay, any other questions? I'll stop sharing and stop recording.